Okay, welcome back. So we are trying to understand why optimization, and we said that the reason why we need optimization is to convert data to decisions, right. So in machine learning, why do we care about optimization? Well, one way to answer this would be to say that we always care about finding, let us say, for example, if we are in supervised learning, we care about finding the the best classifier. Right. So there are different ways to classify, let us say, an email as spam or not spam, and given a data where some data points are spam emails and some data points are non-spam emails, and now given a new email, you want to understand whether this email is spam or not, and there are so many classifiers that can take an input email and then classify it as spam or not spam, but somehow we need to understand which is the best classifier. Right. So there is this notion of best that comes in, but then best is kind of a vague notion, I mean, just describing it like that. So we need to understand what do we really mean by best, right. So often when I say best, it means that, well, there are multiple ways of describing best depending on what you want to do. One particular example could be the best classifier is the one that has some kind of least loss, right. Well, you define something called as a loss, and then among all possible classifiers, you look at the classifier that has the least loss, and the one that has the least loss is what is called as the best classifier. Of course, now that begs the question, what do you mean by loss, right. So, well, the specific way of defining loss will depend on what problem you are looking at, what specific paradigm in machine learning you are looking at, and so on, and that is not the goal here, but I wanted to give a brief view that, well, in machine learning you are always after the best something. It could be a classifier, best representation for data, whatever it is, and in some sense the best would translate to either the least something, it could be least loss, or in some cases it could be the maximum, well, reward. And again, I am not defining what reward is here, it depends on the problem at hand, and we will see a lot of examples as to what this loss could be and what these rewards could be as we go along in this course, right. For the moment, let me leave it at that and say that optimization is extremely fundamental to understand machine learning algorithms, because machine learning algorithms always want to make a decision in the best possible way, and best is either minimizing loss or maximizing reward and things like that, right. So there is always a least or maximum that comes into picture. Okay. So with that introduction to why optimization is relevant to machine learning, now we are going to take a step back and understand the basics of optimization itself, right. So what does it mean to say you are optimizing something, and how do you optimize it, right. So what is the algorithmic way to go about optimizing whatever we want to optimize. Okay. So to do this, we are not going to think about machine learning at this point. We are going to think about a more broad framework of optimization, and we will try to understand optimization in a more general way. Of course, we will relate it to specific machine learning problems as we go along in this course, but for the moment we are going to step back a bit and say that, hey, I am going to understand optimization itself as a general mathematical approach, and then we will try to apply it to machine learning problems. Okay. So with that, let us start with a simple example, and I hope this example will illustrate the the different different things that one needs to keep in mind while coming up with an optimization problem. Okay. So the example is a cooked up example, nevertheless it illustrates what we want to do very well. So let us try to understand what this example is. Okay. So let us say you have a field, right. So an acre of field, let us say this is like a square field, which we are going to think of this as a 2x2 grid, where the left bottom part is what is the origin, right. So it is the point 0, 0. Now what happens in this field? Well, at some point in this field, let us say the point 20 comma 30, there is a cow, right. A cow at is at 20 30, right. So this is the point which corresponds to 20 on the x axis, 30 on the y axis, and that is the position of a cow. Now what is this cow doing? So well, the cow is tied to a, let us say a rope, right. So cow tied to a, the cow is tied to a, let us say 10 unit radius rope, right. So there is a rope that you have tied to the neck of the cow, and the length of the rope is let us say 10 units, in whatever units we are measuring this field's length itself. What does that mean in this picture? Well, if the cow is at 20 comma 30 and if it is tied to a rope at which is of length 10 units, then where are the positions where the cow can reach in this field, on this field, right. So pause for a second and try to think about that problem. It is not hard, but I would encourage you to pause and think. Well, because the rope is 10 units long, the cow is going to is going to be able to move 10 units in any possible directions in the field, right, and it cannot move more than 10 units. Okay, so let me make this slightly larger to make the point clearer. Yeah. So now if you want to understand the set of all points where the cow can move to, well, it is going to simply be a circle. Oops, my circles are bad, but hope that should be okay. Anyway, imagine that is a circle and of radius 10, right. So that is where the cow is allowed to move, simply because it is tied to this rope which is 10 units long. I am going to erase this part and just leave the circle there. Okay. Now what else? What else is happening in this picture? Well, the other thing that is there in this picture is that there is a perpendicular fence, right. So there is a perpendicular fence that passes through let us say the point 30, or rather let me say, let us say the point 25 0, right. So there is a perpendicular fence. Now let us try to understand that in this picture using a different color. So there is a perpendicular fence, let us say at point 25 comma 0. So this is 25 0, and of course the previous point is 20 0. Now how does the perpendicular fence look like? Well, it is going to look like this. It is going to be a straight line, and because of this fence, the cow will not be able to move further away from this fence, right. So that is another restriction, so to say, on the cow. Okay, so now where are we getting at with all this? Now I am also going to say that there is one more point here. So there is some grass on the field at, let us say, the position 40 40. Okay. So where is 40 40? Well, 40 40 is somewhere here, and this is grass. This is the position where you have grass. So this is the setup. You have a cow, and the cow is tied to a rope, and there is a perpendicular fence running at some point in the field, and there is grass at some point in the field. Now in this setup, the question that I am going to ask is, how close can the cow get to the grass? Right. So this is the question that I want to answer, right. So which means that the cow is allowed to move wherever it is allowed to move with its restrictions with respect to the rope and the fence. With these two restrictions, it can reach to some point where it is closest to the grass. Maybe it reaches the grass itself, well, in that case it will eat the grass, otherwise it will reach as close to the grass as possible, right. So, now the question we are asking is how close can the cow get to the grass, and we want to understand this in a more mathematical framework, and that is what we are going to do next. Okay. So, we have set up the problem. So, now we want to understand what exactly are we measuring, right. So, what are we measuring? What is our goal, right. So, what are we trying to find? Well, the question asked was how close can the cow get to the grass or the fodder, which means that we are measuring distances in some sense, right. So, and what is exactly the distance that we are measuring? Well, we want to measure the distance from the grass, right. So, the distance from grass, that is what we are trying to measure, and of course, we said that the grass is at 40. Now, for any position x comma y of the cow, or let me call it x1, x2 of the cow, we are trying to measure how close it is that position to the position 40, 40, right. So, say cow is at the position x1, x2, right. So, where x1 is the horizontal axis and x2 is the vertical axis as measured from the origin that we looked at earlier. Now, if the cow is at x1, x2 and we want its to understand its distance from the grass, which is at 40, 40, well, how do we find this distance? Well, the 40, 40 point is somewhere here, 40, 40, and let us say the cow is at some x1, x2 and we want to understand what is this length, right. Right. So, how much is this? Well, this is easy to compute. So, this is simply the distance of x1, x2 comma 40, 40, and I am sure all of us has seen this at some point in our schools. So, this is simply x1 minus 40 squared plus x2 minus 40 squared. Of course, there is a square root there which will be the distance, but let us think of this as the squared distance, which means that it is simply x1 minus 40 squared plus x2 minus 40 squared, right. So, now what do we want to do with this distance, right. So, the next question is what do we want to do, right. So, what to do with this distance? Well, our goal is to make this distance as small as possible, right. So, that is our goal, because we want the cow to get as close to the grass as possible, which means that we want the distance to the grass to be as small as possible, which means that we want to find that position of cow which will have the least distance to the grass. Well, if you think of the position of cow as x1, x2, then the distance to the grass is exactly what we just gave. So, which means that our goal then, let me write it here, is to minimize over x1 and x2, x1 minus 40 squared plus x2 minus 40 squared. Well, is that all it? Right. So, if I had to find the answer to this problem, it means that I am asking, well, the cow is at some point, but then how close can it get to the grass? I have not taken into account the rope yet, and I have not taken into account the fence yet. If I do not take that into account, of course, the cow does not have a rope and there is no fence, when of course, the cow can reach the grass itself, which means that the answer to this would be the minimum distance is 0 and the point is 40, 40, right. So, but then we do have some restrictions on the movement of the cow, and we have to somehow incorporate those restrictions into the problem. Well, there are two restrictions. The first restriction is what we call as the the rope restriction. The second one is the fence restriction. Let us try to understand what is the rope restriction do to our problem. Well, the rope restriction, the rope restriction would tell me that I can't choose arbitrary x1 and x2 as positions of the curve, because the rope is restricting me only certain x1 and x2 where the curve can actually be present, right. And these restrictions, we know that if the curve is at 20, 30, then the rope restriction would only allow me to move to a radius of 10 units, right. So, which means that how do I mathematically formalize that? I formalize that by saying that whatever x1, x2 that I finally find as answer, it necessarily has to satisfy x1 minus 20 squared plus x2 minus 30 squared. Well, what am I trying to say? I am trying to see what is the distance from 20 comma 30, right, which is the initial position of the curve, to where all it can eventually end up with, right. So, we know that it has to be in this region of the circle, which means that this value necessarily has to be less than or equal to the square of the radius, right. So, in this case the radius is 10 units long, so which means that this is going to be less than or equal to 10 squared, right. So, this is what the rope restriction is forcing me to choose an x1 and x2 with certain constraints, right. So, this is the rope restriction. Of course, there is one more restriction, which is the fence restriction. Now, what is the fence restriction say? The fence restriction says that there is a perpendicular fence that runs at the point so 30 that runs through the point 25 comma 0, right. So, which means that if I have to convert that into an equation, now what does the fence restriction tell me in terms of x1 and x2, the set of all positions where the curve can potentially could be. Forgetting the rope for the moment, if you only focus on the fence, well, the fence is passing through 25 comma 0. Well, it can be, the curve can be anywhere on this region, in this region, right. So, that is what the fence restriction says. It cannot pass the fence, which means that it is okay to be anywhere on the left side of the fence. Now, how do I codify that in terms of equation? Well, I would simply say that the fence restriction says, well, the only restriction that it is putting me is on the horizontal axis. I do not care where the curve moves in the vertical axis, at least the fence does not restrict the curve's movement in the vertical direction, it only restricts it in the horizontal direction, which means that the restriction is that x1, which is the horizontal direction in which the curve can move, has to be necessarily less than or equal to 25. Okay, good. So, now we have converted our problem into a mathematical problem which can be solved, right. So, we have the problem as follows: minimum x1, x2, x1 minus 40 squared plus x2 minus 40 squared, such that two things happen: x1 minus 20 squared plus x2 minus 30 squared is less than 100, less than or equal to 100, and x1 is less than or equal to 25, right. So, now this is an example of an optimization problem. Now, we have set up the optimization problem. Now, we will understand it in a more general framework next. Okay. So, now we are going to understand whatever optimization problem we just set up in a more general form, right. So, the general form of an optimization problem then is as follows: we want to minimize some function of x, right. So, this x can be, in general, let us assume this x can be anywhere in Rd, the d-dimensional real space. In the curve example, this was a 2-dimensional space. In our example, it can be anything, right. So, in the general form, it can be anything, x can be Rd. Now, we also had some restrictions on the moment of curve. Now, that will translate in the general form as, well, there are some constraints on what x could be, and one way to say this is to say that there are a bunch of constraints, functions, which determine where x can lie, right. So, and these constraints in this case are g1 of x is less than or equal to 0, g2 of x is less than or equal to 0, and so on till gk of x less than or equal to 0, right. So, in the previous example, in the curve example, there was only there are only two constraints. One was the rope constraint, other was the fence constraint, which means that G1 of x would be the rope constraint, and let us say G2 of x would be the fence constraint. In addition to this, there may be problems where you also have a constraint which is not a less than or equal to constraint, but it might be a equal to 0 constraint, right. So, the constraint could be Hj of x equal to 0 for all j equals 1 to L. Think of it as maybe you have a specific value for a budget and you want to spend that much amount, and that can be, for instance, codified as an equality constraint, right. So, this is a very general form of an optimization problem. Now, it has a lot of components. Let us just give these components names so that in our interaction as we go along, we will use these names so that it becomes clear what we are talking about. The function that we are trying to minimize in this case is what we will call as the objective, right. So, what is our objective in the previous case? In the cow example, our objective was to minimize the distance to the grass, right. So, that was our objective. Now, the value that you will eventually end up finding, right. So, your parameter of interest is what we will call sometimes as variable on which you are optimizing, or sometimes it is also in machine learning parlance, this will also be called as a parameter, right. So, in the case of the cow example, again this is the position of the cow, right. So, and that was a 2-dimensional parameter. In general, it could be any d-dimensional parameter. Now, what are these? Well, these restrict the value that the parameters can take, and we are going to call these as constraints. Specifically, we will call the constraints where j of x is less than or equal to 0 as inequality constraints, and the case where j of x is equal to 0 as equality constraints. Now, here is a quick question for all of you. Well, the way I have written this has a certain form, right. So, I am trying to minimize an objective subject to certain inequality and equality constraints, and the inequality constraints are always of the form j of x is less than or equal to 0, and the equality constraints are always of the form hj of x equal to 0. Now, in the cow example, there was no 0 on the right hand side, right. So, we said that the inequality constraint was that the distance, the cow is tied to a rope which is of radius 10, and we converted it to an equation. Now, this is what I am claiming as a general form, what you are seeing now. Now, the question to you is, can you always put any inequality constraint into this form and any equality constraint into this form? That's a simple question, but then think about it. The second question is that the form that we have stated here is an objective which we want to minimize. In some cases, if the objective is reward, you might want to maximize it, right. So, now do we need a separate whole theory for that, or do you think is it possible to convert a maximization problem into an equivalent minimization problem? If so, how would you go about doing it, right. So, think about that as well, right. So, these are two questions for you to ponder and think about. Okay. So, with that we have given the general form of a optimization problem. Now, it begs the question, well fine, now we know how to convert our problem into an optimization problem. We understand the basic structure of an optimization problem. Now, how do we solve the problem? Right. So, that is the most important part. Well, I know how to set up the cow's problem as a proper mathematical question, optimization problem in the general form, but how do I go about solving this, right. So, how do I finally get the answer? What is the algorithm to get the answer? And that is what we are going to start developing next.